Now I want to explain this amazing article, Attention Approximates Sparse Distributed Memory. This paper by Trenton, and he has another beautiful article which relates this sparse distributed memory to continual learning. Both of these articles are very important for many reasons. And there are also other interesting papers, these positive samples, very similar ideas. And for example, the Carnival machine, this one, considers your memory, that memory matrix that I told you in hybrid machines in DeepMind company. They use the Carnival machine idea. It treats this matrix as a latent variable, and therefore they work on Bayesian analysis and those things. So let's focus on this article in 2021, which Attention Approximates Sparse Distributed Memory. So there is a link between SDM and attention. Abstractly, the relationship between sparse distributed memory and attention exists because SDM's read operation uses interaction between high-dimensional hyperspheres that approximate the exponential over sum of exponentials, that is, attention's softmax function. SDM provides an algorithm for how memories or patterns, if you remember my playlist for Hopfield networks, we had patterns, and we had limited capacity, as you know. We computed the capacity. So SDM provides an algorithm for how memories are stored in and retrieved from neurons in the brain. And in brain, hippocampus plays an important role in these associative memory, as well as cognitive map theory and many other tasks. There are three primitives that all exist in the space of n-dimensional binary vectors. Patterns that you are familiar with. We have two components: the pattern address, just like previous articles, the pattern address, which is the vector representation of a memory, and a pattern pointer, which is bound to the address and points to itself when auto-associative, or to a different pattern address when heteroassociative. So a heteroassociative example is memorizing the alphabet where the pattern address for letter A points to pattern address B. B points to C, and like this. So for tractability in analyzing SDM, we assume our pattern addresses and pointers are random. So we have M patterns. For example, A associates B, B associates C, and you're thinking now. Your brain is associating different things, and 1,000 of these iterations happens until you understand something. But they happen very fast. And then we have another primitive, which is neurons. But neurons in this context is like, if you want to implement it in brain, if you want to compare it with the brain, it's like a region of the brain. For example, a small region of your neocortex could be, for example, nowadays we model whole brain networks with mean field theory and Wilson-Cohen model and those things, which are very important for computational neuroscience as well. So neurons in this paper is a little bit different from what you know. It is they define it differently. There are neurons with fixed addresses that store a set of patterns written to them, but each neuron will sum over its set of patterns to create a superposition. This creates minimal noise interference between patterns because of high-dimensional nature of vector space and enables all patterns to be stored in an n-dimensional storage vector constrained to the positive integers. Their biologically plausible features are outlined in these references, and when we assume our patterns are random, we also assume our neuron addresses are randomly distributed. So what is a query? Query is the input to our SDM, to our sparse distributed memory. So we have a query which is a vector of 0 and 1, but we have n of them. And the goal is the best match problem is to return the pattern pointer stored at the closest pattern address to the query. I don't think it is biologically plausible because in biology, in your brain, the best thing that you can model is lots of spiking neural networks. And because we have many of them, it's better to look at it as a statistical model. I mean, the average of, for example, activations. This is much better variables. And also it is very important to relate excitatory neurons to inhibitory neurons. Otherwise, your model is not plausible, biologically plausible. And so this, for example, we have 20% of your neurons are inhibitory. They try to stabilize this excitatory, which is roughly 80% of your neocortex, if I'm not wrong. So here you want to write into nearby neurons. So the top row, this row says that top row, 3 patterns being written into nearby neurons. So first, this is step 1, the first write operation, and then second, patterns are stored inside nearby neurons and the original pattern location is shown. And then in third, writing a second pattern. So when I activate, when I say this, write this, it activates all of these nearby neurons. And then when we write in a second pattern, we want to write another pattern. For example, we want to write B, I mean the pixel, this image. Then you write it here, for example, and nearby neurons are activated, and like this. So when you have a query, the circle intersections with original pattern locations is like this. So in the bottom, like here, the bottom row shows 2 isomorphic perspectives of the read operation. Neuron view, I mean left, shows the query reading from the nearby neurons with the inset showing the number of times each pattern is read. The 4 blue patterns are a majority, which would result in one-step convergence. So the 4 blue patterns, these 4 blue patterns, are a majority which would result in one-step convergence. So for connection to attention, we focus on STM read operation. This is what you need. So you know the Hamming distance, and so within a Hamming distance, I can say that your X is just a linear combination, just sum of all pointers. These P are pointers. These are pointers. If you sum all pointers that are within a distance D, so all of the neurons that within the distance D, you sum all of them. And this is how you write. And having stored patterns in a distributed fashion across nearby neurons, STM's read operation retrieves stored pattern pointers from all neurons within distance d of the query and average them. So we've got these neurons, and now we add them and then we average them. So this average is effectively weighted because the same patterns have distributed storage across multiple neurons being read from. The pattern weighting will be higher for those patterns with addresses nearer the query because they have written their pointers to more neurons the query reads from. Geometrically, this weighting of each pattern can be interpreted as intersection of radius d circles that are centered on the query. So this is how you have 2 to the n possible neurons that have both stored this pattern's pointer and been read by Kisi. And so this O here, that you see it everywhere, this O is just the set of all possible neuronal addresses within radius d of Kisi. So the read operation sums over each pattern's pointers, and so this is just but this is the cardinality of that. When we say this of set, this is a cardinality. We are just counting how many of them are in their intersection. Because intersection of Kisi with D with radius D and PA with radius D, this is pattern of A with radius D. This intersection, if you count the number of neurons and then divide it by all of them, but here we are not using P of P. So this is how they define the query, how they define Kisi of new. So this is how you read. And this G acts element-wise on vectors. And the denominator just normalizes all the weights, so they sum to 1. But G, it's either 1 or 0. And also it normalizes. So the output of STM read operation is written as updating Kisi to Kisi new so that it can be applied the read operation iteratively if full convergence to its best match pattern is desired and was not achieved in one update. The circle intersection is calculated as a function of Hamming radius for read and write operation. Of course, you can use any other distance, for example, dot products, not just Hamming distance. But in this article, they focused on Hamming distance. And the Hamming radius for read and write operation, the dimension, and the vector distance between the query and the pattern. This is the vector distance between the query and the pattern, this distance. So this equation 2, sums over the number of possible binary vectors that can exist at every location inside the circle intersection. And we can, there in the appendix, they showed that they can approximate it like this. And so these are the neurons at the intersection of your pattern and your query. And finally, this is how they relate it to attention. If you're familiar with my playlist for transformer architecture, I explain that query, value, and key, these matrices, I explained them. These are the same thing here because they are using the idea of transformer. We have a couple of matrices, And then our C nu, it can be calculated like this. So K, V, and Q symbolizes the Q value and query matrices. And Q is a single query vector, and Y represents the raw patterns to be stored in memory. The bad thing about this transformer architecture is because it's computationally expensive. That's why I have a playlist for RNN dynamics, and also I have many playlists about LSTM, GRU, and those things, those traditional things, that they are very important because you can do many things with them. You don't have to worry about how many tokens, what is the length of your sentence, and those things. And because the computational complexity is much smaller than the transformer architecture. So transformer architecture is not for everything. We still need to come back to our beautiful BiLSTM, BiGRU, and those things. Even gated, when we say gated recurrent unit, it means it is more biologically plausible. And there are other things as well, such as reservoir computing, that you randomize the weights of input and the weights of reservoir, and you just design the weights of output, which is just a linear regression. It's very fast. So there are lots of alternatives to transformer architecture, and we don't need to just focus on one thing, one paradigm, because we lose the opportunity to find new beautiful paradigms that are more biologically inspired, biologically plausible. Because if we draw inspiration from our beautiful brain, our algorithm will be much better than if we just draw inspiration from from engineers, that each one has a different bias. But our brain is like a miracle. We have 85 billion neurons, and nowadays there is a new branch that learns these different regions, and it's called connectomics, and you model statistically, because you have many of them, you statistically model and relate them to each other. For example, what the relation between prefrontal cortex and hippocampal and amygdala and basal ganglia and many other regions, and you connect it, and each one is a set of recurrent neural networks, and you can design new algorithms. But this article has had very interesting things as well, but it may not be biologically plausible. And so these ideas come from sparse distributed memory, goes back to 1982, and we still have these papers. These are very beautiful papers, and look at this, that we have many interesting articles.